Now let us try to understand the black box, which I earlier mentioned what it means by black box. So basically this uh, black box method black box can be defined based on the type of machine learning that we choose. It can be of three types: supervised machine learning, supervised ML, unsupervised ML, and another different type of machine learning is reinforcement learning. So in supervised machine learning, we pass both the input and the ground truth. Basically, we have something called labeled data or annotated data, and we develop learn in a supervised fashion, telling the model, look, this is the input and this is the output. You have to predict in such a way that the output predicted output should be as close as possible to the ground truth. In unsupervised, as the name suggests, it's the opposite to supervised. You only pass the only the input data. There are no labels involved in it. It's unlabeled. It operates under unlabeled data. Reinforcement learning is a entirely different way of learning altogether. It's called agent based learning, where the agent tries to learn something called environment by taking some actions and getting a reward. So if it takes the right actions, the rewards will be positive, and so, so right actions lead to positive reward and wrong actions lead to negative reward. So the agent is supposed to learn in such a way that the overall reward is maximum. Now let us understand in a discrete and continuous ways what are the different types of, how does this supervised and unsupervised learning methods lead to. So supervised ML, unsupervised ML in a continuous and a discrete data space. So under supervised ML and continuous case, we have task called regression, and supervised ML, and in discrete case we have classification. Unsupervised continuous is basically dimensionality reduction, and unsupervised discrete case we have something called clustering. So each of the individual tasks here again defined with own models, specific models that can help in doing these individual tasks. Now another one way we have understood the black box, the model types of models involved inside this black box based on the type of machine learning we want to do. Another way of looking into this black box models is based on the tasks. So in a very broad terms, one thing, and in a computer vision domain or NLP speech, we can discuss the task in such a way, and I'll explain the types of models currently available. So let us take an example of an image which you can see on the right. Let's say it's a dog image. I'll try to draw a dog. Right. So we are trying to, I'm giving an example of supervised machine learning where we have a label of this image which is a dog. Now first task is classification, which is in this case an image classification. So basically the task is to classify, give an input as this entire image. The model should predict it as and give label it as dog. So for doing this, we have something called CNNs or convolution neural networks. So the types of models involved here are, we have VGG16, ResNet 18, 51 layers, 101 layers. These numbers indicate the number of layers in that convolution neural networks. Inception V3, GoogleNet, AlexNet, ResNext, and so on. So the main task is to learn the feature representations of the individual image of the input data and try to classify those features into the respective labels. So this is the task, pretty much the task of image classification and the types of models we can use in this black box. Next, we have a next level of upgrade to the classification task, which is also called, which is detection. It's also known as localization. Now if you take the same image dog example, so the in the first task we are trying to classify the image as any of the label. It's a dog, so it's a label dog. So we are trying to classify the entire image into something. Now next we want to identify within the image where exactly is the object present. So it's a task of localizing. We are trying to identify or trying to localize or trying to dig into deeper understanding of where exactly the object is present. So for doing this, we can there is a way of doing this is, which is by trying to draw a bounding box around which where the object is present. So it pretty much tries to localize that, look within this image which is of dimension, height, cross width, we have an image at this location which is given by x1 y1 top left coordinates and x2 y2 bottom right coordinates. So now we are trying to learn these coordinates. Basically we are trying to do regression and identify these coordinates in a and learn where these coordinates actually exist, fall under within that image. Now for doing this detection task, which is also called as object detection, sorry, so we have models like YOLO, you only look once, version 1, version 2, I think now it's in version 7. I call it a YOLO family. So basically these are called single stage architectures. or models as they predict the bounding box in one pass, so they are called you know single stage architectures. On the other hand, we have faster RCNN models, which is a two-staged architecture, as it has two main components that sequentially work basically. So we have something called region proposal network in this, just RPN, and a region based convolution neural network, which is RCNN, as the name suggests. So the reason behind the single stage and two stage is there is this trade off called accuracy or performance in correctly detecting the objects versus real time. So given an image to input image to model, it should detect in as real time as possible within 11 milliseconds. And when we want it to be more real time, the model should be lightweight, and to do it lightweight we can reduce the number of layers, internal layers. And if we reduce the number of internal layers, that will affect the performance, because we are shallowing the or reducing the number of layers, then the feature representations and all these will be affected, and the overall performance is affected. So when I say lightweight and reducing the number of layers, basically single stage architecture will be helpful in this scenario to be more real time. And if we compromise on accuracy a bit, then single stage architecture definitely will help us in this scenario. For example, real world applications, if you see autonomous vehicles or self-driving cars, they have to detect the objects on the road or the road elements, persons, bus, cars, traffic lights, pedestrians, or poles, traffic signs, everything in real time. They cannot wait even a minute or fraction of seconds to get from the model. They cannot wait to get the output from the model, otherwise it would have already met with an accident. So their real time performance is a necessity. On the other hand, in applications like medical or healthcare, even if you provide your data and ask the model to accurately detect where the segmentation, or sorry, where the tumor exists within that data, so you can wait for 1 or 2 days, but there the performance is very important, because false positives in medical domain is highly, you know that can highly drastically affecting the patient's diagnosis. So their accuracy is very important, and we can opt for methods like a two-stage architectures in that scenarios. So that's why there is a trade-off, always a trade-off between the accuracy and the real-time performance. Now